So I like to give a mini review of the Brownian motion of a Brownian particle. I think this is the basis of polymer dynamics. Before we understand polymer dynamics, we need to have a good control of concepts of Brownian motion. You have the handouts, right? We went through this before, but I'm going to make a quick summary of the basic features of a Brownian motion once again. Right? So I'm going to share the screen. Okay. So we have consider a particle, a large particle of, say, mass m. And let's say the radius of this particle is r. And this is in a liquid, right? This particle is in a liquid. With a viscosity eta 0. And this is also at a temperature T. So this is a situation that we like to address. Right? There is a mass of this particle, rigid particle. Let's say this is rigid. As an example, let's take this to be rigid sphere. So there are characteristics of the system, right? What are the characteristics? The particle has a mass m and a radius r, and this is in a liquid with viscosity eta 0 and temperature T. And the question that we like to understand or answer is, what is the displacement of this? That is r, the center of mass. How does this position move? That's a vector. As I have drawn in here, it is at this point. Little later, this particle is going to be perhaps somewhere here. And we like to know what is this displacement. This is at 1 time t, the minus a 0 time. What is this number? Okay, how much is the displacement after an elapse of time t? And it turns out this is not an easy question to answer for realistic situations. When I say realistic situations, I'm talking about solvent molecules at a temperature T, and the solvent molecules are not fixed in space. They move around. And in fact, we always have lots of collisions. This molecule, right, would collide. This solvent molecule, for example, will collide with this particle, and this solvent molecule will collide. This molecule will collide, and then this will get out, collide, because it cannot penetrate. It will go, hit, and then return back. Hit, and then return back. And they are not working together. They are independent. When this molecule hits this particle, other molecules do not know that. As a result of this, we create this kind of collisions, create a random force. Net random force on the particle. If I have a random force acting on a particle, what do I mean by random force? That means at a particular time, I do not know exactly what the force is. It's unpredictable. It could be a positive direction, or because this hits there, therefore it could be negative direction, opposite direction. So we do not know the magnitude and the direction of this random force. If we do not know that force, then we cannot calculate this quantity precisely, because this quantity then depends on at what time, what particular instant I'm going to look at it. And we know that since this random force is so quick in terms of correlations with itself, for that particular random force, I will not be able to see any movement at all. So I have to wait for a long time to see the movement of this particle. Therefore, we can do this when in the presence of random force, then we can do it only in an average sense. That is average over all possible realizations of random force and at a particular temperature. So we can define only in terms of, we can define this only in terms of quantities like this. Average. So we say average over noise. We say noise because it's a random force. And why does a random force arise? This solvent molecule is not fixed in space. It's not frozen. The solvent is not, so if you take water, the solvent is not ice. The solvent is water. Why, therefore, if it's a liquid, the movement of this solvent molecule depends on temperature. See, this was an earlier question during the question time earlier, right? You asked, does the random force depend on temperature? Indeed, it does depend on temperature, because if the temperature is 0, the molecule is not going to move. The solvent molecule is not going to move. Therefore, it will not create any random force. So when I say average over noise, I mean average over thermal noise. Because it depends on temperature. And the question is, okay, what's the answer to this? We need to know what is the answer to this quantity. That's what we are interested in. Why do we ask this question? It's obvious, right? Because we want to look under the microscope, we see how much it moves, where does the center of mass of the particle moves. Now I want you to contrast this situation with a Newtonian problem. This is a real problem, right? This is a real problem. In contrast, consider a particle, a rigid particle, again, a rigid particle, same, mass is m, radius is r, right? And I have a friction against it. Suppose I put a force, a deterministic force. Let me write F, deterministic force, and I'm going to drag it through, suppose I have a surface and I have a particle, and then I pull it on a surface, like an automobile on a road, right? Suppose I'm pulling it, deterministic. I put a force. I press my gas pedal, then I'm exerting a force for the car to move. And then there is a friction against the medium. Okay, so that friction is going to, there is a frictional force which is against the movement, right? Given this deterministic force and there is a frictional force, we can compute an answer for this. Right here, I do not need to have these angular brackets because there's nothing to average you over, because this is deterministic. Right? This is deterministic, it's not random. And this is Newtonian dynamics. In contrast, the top panel, this one, is Einstein dynamics. Or commonly known as Brownian dynamics. So there are two classes of situations. Here, a realistic situation where solvent at finite temperature is creating a random force on this particle, and we want to understand what happens in here. And in here, in contrast, we in the Newtonian dynamics, where your force is deterministic, right? Force is deterministic. And then we want to look at, again, the same question. What is the center of mass as a function of t at a particular time with respect to center of mass position at an earlier time? What is this? And here, please notice, I'm not putting an average because we know exact answer for this. And I told you, if you write simple Newton's equation, suppose I have the situation right, mass of the particle times the acceleration, d square d by dt square, center of mass, a vector, center of mass position. And then I balance it with, say, frictional force, for example, right? When I balance it out, that's equal to this Newton's equation, right? This is Newton's equation. Force is equal to minus friction coefficient times velocity dr, center of mass by dt. If I have something like this, then I know we can solve this. This is basically mass times the d by dt of velocity of the particle, and that's equal to minus zeta velocity. This is a linear equation, right? This is a linear equation, and you can solve this equation. Given an initial velocity v0, we can solve this equation. If you do that, right? If you do that, the velocity at a time t is equal to velocity at 0 time e to the minus zeta over mt. You can satisfy, make sure you can take this equation and take the derivative, right? You will see, for example, I put a dv by dt. If I do this, this term does not depend upon time. Therefore, that's v t is equal to 0. And the derivative of an exponential, right, d by dt, e to the minus that one, that's equal to e to the minus zeta over mt times minus zeta over m. Right? Minus zeta over m. Just derivative, taking the derivative. Okay, so now we go back to the Newton's equation, put the m times dv by dt, that's equal to, I multiply by m, so I have minus zeta here, and this quantity is above here, the same as vt, so I get to v. So mass times acceleration is equal to minus zeta times velocity, and that is this equation. So basically, I'm just showing you, we solved this equation correctly. This is what we want to solve, and it's trivial to solve, and that's the solution. So we got the solution. Deterministic, we know the velocity. And then we can calculate this quantity, displacement, and you know that velocity is equal to displacement by time. That's the velocity. Therefore, position of the center of mass at time t minus position of center of mass at an earlier time, that's equal to, that is the displacement. That's equal to velocity times time, but that time duration from 0 to t. So this becomes 0 to t, and dt prime, that's a dummy variable, integration variable, times velocity at t prime. the t prime is from any time during 0, 1, 2, 2, up to t. So if I know the expression for velocity, I take the velocity and put this in here. Again, it's an exponential integral, right? dt prime e to the minus zeta over m t prime. Now we can do that calculation. If you do that, you get substituting. So this is equal to d t prime 0 to t. V t prime is v0, right? This is t prime 0, 0, of which I could write to be simply v0. And then e to the minus zeta over m t prime, right? That's t prime. D t prime, v t prime is I put this t as a t prime. Now this is a very easy integral to do, right? V at t is equal to 0, earlier time. And then I have e to the minus a t integral of dt, therefore negative 1 over a e to the minus at, take the limits. If you do that, you get m over zeta times 1 minus e to the minus zeta over mt. Doing that integral. Okay. And then that's the displacement. So there is nothing to average over, right? It's a deterministic, it's exact. So if I plot this quantity, the displacement, as a function of time, for early times, you can expand this, right? E to the minus at would be 1 minus at plus a squared t squared by 2, etc., etc. And then I cancel out the leading terms, right? Then what you get is you get a curve like this. It goes straight line like velocity, right? The slope of this is essentially initial velocity, and then eventually it saturates and it doesn't go anywhere. It gets to a final value because when t is very large, this term goes out. Therefore, I have only v0 times m divided by zeta. So that's the final answer. Okay, this would be v0 m over zeta. So the place where it stops, basically the displacement, right? First, for short times, it keeps going because I had an initial velocity, right? Initial velocity I had. That's why the particle is moving. I mean, right? I'm dragging this. Therefore, it's a straight line. The slope is a velocity, but eventually it will stop moving. So I call this to be immobile. According to this Newtonian argument, this is immobile. Particle does not go at all. All right. And please notice, where does it stop? It stops at this value. So in this process, Newtonian process, mass m plays a role. And please notice, r, the radius, is not showing up. It's the mass that plays a role. Okay, right? If it's a smaller object, it's a small mass. When I say smaller object in terms of mass, small mass, then it will stop at a shorter distance. If the mass is big, it will stop at a longer distance. So mass matters in this situation in Newtonian dynamics. All right? I said mass here, radius here. The radius is not playing a role, right? In the deterministic problem, mass is important. Okay, mass plays a role. And one important question that I wanted to emphasize again is, when does the transition from this behavior to that behavior occur? Where is the transition? From the cartoon that I have drawn, the transition will take place somewhere here. That's the transition point. So when I say the particle is going to be immobile, I need to have a measure of time. At what time I would get the particle to be immobile? At what time the particle will still keep going? Okay, that is given by this location, where this changes from this behavior to that behavior. Let me call that to be tau. And that tau turns out to be, based upon this exact calculation, and that tau turns out to be m over zeta. Because that's what is appearing here, e to the minus t over tau. I can rewrite this to be e to the minus t over tau. Tau is m over zeta. Okay? So that's the characteristic time for this deterministic problem. So if the time is shorter than this tau, the particle will undergo motion. If the time is longer than this, it will be stopped. The particle doesn't go anywhere. This is the Newtonian dynamics. And before I go further, I want to emphasize again, for all of us, it's much easier to identify this boxed equation without doing all these calculations, right? When we did the exact calculation, look at this derivation here. We started from this equation, we solved that equation. Started from this equation, we solved that equation, given the initial velocity. This is high school physics, right? We did this, right? I'm sure you must have done so many calculations of this type in high school, right? So when you do these things, you are able to get an understanding of what the characteristic time is, which is an important quantity for any problem that we deal with. Polymer dynamics, galactic dynamics, whatever problems we are talking about, right? There is always a scale for any particular process. That scale tells us an indication. It gives us an indication about what is short time and what is long time. When we say short time, that is by itself is not a meaningful statement. We have to say with respect to what. Similarly, when you say, oh, wait for a long time, with respect to what? That with respect to what is this number. If the time variable is less than this quantity, we say short time. If this time is larger than this quantity, we call this to be long time with respect to that characteristic time. How do we get this characteristic time? I go back to this equation once more. So let me show this. Mass dV by dt, right, is equal to minus zeta v, right? Just remind you, right? Mass times acceleration is equal to force. It is a frictional force. So let me rewrite it once more. dV by dt is equal to minus zeta over mv. I divided m throughout. And I write this once more. dV by dt is equal to negative v in the numerator divided by m over zeta. So I brought the zeta friction coefficient downstairs. So I rewrote this zeta over m as m over zeta in the denominator. So I look at this shape. Look at, I call the shape of the equation. This says, in English, it says velocity at the numerator divided by time in the denominator. On the right-hand side, forget about negative sign, velocity in the numerator and time in the denominator. It must be time, right? I cannot have any other unit, because if I have an equal sign and the numerator is velocity and velocity here, and on the left-hand side, the denominator is time, then this quantity that appears here must be time, right? And given the shape of the equation, this time is equal to m over theta. So it sets, the equation sets the scale. This we call to be the characteristic time. Characteristic time, tau, characteristic time for characteristic of this equation. Once you write this equation, the characteristic time for that particular process is only this number, nothing else. And naturally, when you do the calculation, same thing happens. That's the natural time. Okay. And you can see this, that's a natural time. Here's velocity times, right? Velocity times the time, right? That gives me displacement. Again, unit wise, right? This is also time. That's also time. That's the characteristic time, right? Okay. So that's the end of Newtonian dynamics. Okay. This is again a repetition, but I hope it's very clear. So what is the conclusion that we have? The conclusion we have is we decided not to think about this problem right now, because it seems to be quite rich, because the random force, I have to think about taking averages, but I'm interested in a quantity like this, right? And this is the Brownian dynamics. Before that, I wanted to remind myself what will happen if I have a large object. For example, when you are doing an experiment, let's assume you have a beaker, glass beaker. When you take a glass beaker, you put a latex particle into this, some solvent, suitable solvent at room temperature. I put it in, you have liquid there. This problem that we did is what will happen to the beaker. With my hands, I take this beaker and move it, right? That is described by the equations that I talked about here. So that's a Newtonian. There's a large scale mass. If the beaker is heavy, right? If the mass is heavy, if it's, then I need to put more force to move it. If the mass of the beaker is less, then I need only a little force that I have to put to move it. So the beaker on the desktop we are talking about, or your computer, a big computer on your desktop, if you want to lift a massive computer, it's hard. If you want to lift a small laptop, it's easy. So that deterministic problem, because you know how much force you are putting on it. We know how much gravity there is going to be. That is the Newtonian behavior. That is this behavior. That's what we have done so far. And according to this, if there are no external forces, right? And this is the picture. And the displacement is finite. It moves. And with a certain slope, which is velocity related to the initial velocity for short times, for longer times, it becomes immobile. And I showed you the experimental data of Perron more than 100 years ago. He did not observe this. When he looked at a Brownian particle discovered by Mr. Braun much earlier inside a beaker, and he looked under the microscope, he did not see this behavior. And that's the one that launched this problem. Not this problem. This is Isaac Newton's problem and his heroes. So we are now going to make a commentary about this problem, right? Random force problem. How are we going to do this? Okay. So I'm going to return to reality of a Brownian particle. Okay, that means not deterministic. Okay, that's what I want to return to. So we write the equation once again. We write mass times acceleration dv by dt, and there is a friction, right? That's equal to the friction coefficient minus the zeta dv, sorry, v itself. And then here is the force acting on it at certain time t. So this is the random force. Random force from solvent. Because that's real. So now my focus is not on the beaker, on the desktop. My focus is on the molecule, big or latex sphere, Brownian particle inside the liquid at room temperature, at that temperature, which is inside the beaker. That's my focus. Because there are solvent molecules, they are going to be moving around, bombarding this particle. And this equation is an example of a stochastic equation. And more specifically, this is also called Langevin equation. And if you do a computer simulation to solve this kind of equation, we call that to be Langevin dynamics. Okay. This also leads to what is called Langevin dynamics. Okay. As I told you before, we cannot solve this very exactly. Exactly. We have to solve only in statistical sense. Solve the above equation only in a statistical sense. Okay. This means statistical sense. This means, therefore, we need to prescribe the statistical properties of noise or random force. We need to prescribe that. And that is going to be our input. If we make that input, then we can solve this equation. Basically, what I'm trying to say is we are going to say something about this force, with the properties of this force. As was asked during the question time, that force depends on temperature. And in fact, without going into great details, in general, which has been verified by experiments, the average force is equal to 0. Okay, average force is equal to 0 in general, because that's intuitively obvious. When I go back here, every point on the surface of the sphere can be hit by solid molecules. When one molecule hits in this direction, there's an equal chance there's another molecule which hits in here. So when I average it out, since they are all hitting in random directions, it will be zero. Average force is zero. But on the other hand, there is a correlation. The correlation is given by the following formula. F at some time t and F at some other time t prime, a different time, they are correlated. Although the random force at a particular time acting on the whole particle is zero, but the force at one time is correlated with, can be in principle correlated with force at another time. But in practice, that correlation time is so short, we say, on an average sense, we say that is very, very short. Only when t and t prime are very, very close, then they are correlated. Then we call that with delta function, delta t minus t prime. But there is still correlation, but the duration of the correlation time for these noises is so short, we write that to be delta t minus t prime. But the strength of that correlation depends upon temperature. I think this is already I gave you in the last lecture, right? That's 6 kb. Kb is Boltzmann constant, T times zeta. All right. So again, going back to the question that was raised before, does the force, random force, depend on temperature? Of course it does. Look at this equation. The random force, right? If the temperature is very high, right, this correlation function is large. If the temperature is zero, there's nothing. And also the way this correlation of noise occurs not only depends on temperature, but also given by the friction coefficient. Right? It's also given by the friction coefficient that we phenomenologically we assume there is going to be a friction coefficient. In fact, this friction coefficient emerges due to bombardment of solid molecules, because after all, this particle is moving and there is going to be friction. Where does the friction come from? The friction comes from the solvent molecules. So the force that is exerted by the solvent molecules, right, is connected with the friction coefficient. So that's how we write this random force correlation function depends on temperature and the friction coefficient. And this is called fluctuation dissipation theorem. So whenever you have friction, there is a dissipation of energy. And when you have random force, that means it's fluctuating. And as a result, the particle is also moving in a random way. And this in the literature is called fluctuation dissipation theorem. This is an important result. And when you do simulations, for example, we need to make sure this theorem is not violated under equilibrium conditions. This is a theorem. Whenever we say a theorem, we cannot break it, right? In equilibrium, when you put, suppose you write a program, computer code, and you put a random force, which you can get from a random number generator, and you have to make sure when you do the simulation, make sure this is satisfied, right? You have to choose the force and the correlation function in such a way it is compatible with the friction coefficient that you put in here. If you don't do that, you will not get the right answer. So you have to make sure this is what we do. Experimentally, you don't have to worry about it because it naturally satisfies. That's why, that's the beauty of the experiments, right? It's, in equilibrium, this has to happen. And in fact, as I pointed out, this result comes about because of equipartition theorem, right? This is compatible with the average velocity square satisfying equipartition theorem, right? So this is the input, right? We need to prescribe physical properties of noise, and this is going to be the input for our calculation. This is the input. With this input, we are going to take a small break. With this input, we'll come back and look at the consequence of this input on the velocity. Incidentally, before I break, I want to also say that this kind of behavior is called white noise. there are several other situations where the noise is not white. There are lots of correlations. You can have telegraphic noise, you can have colored noise, etc., etc. But in general, for the Brownian particle, the thermal noise, this is coming from temperature. The thermal noise is considered white noise as prescribed by these two equations. Okay. And I think this is a good time. Let me stop sharing this. Let me pause. So I'm going to solve this equation using this input. All right, that's my goal. I use this and solve this. The answer turns out to be, so I don't want to talk about derivation because you have already seen it and it's in the handout, right? The solution is the following. Remember, the first question we want to know is R center of mass at time t minus R center of mass at an earlier time. What is this? Now I have to say in average sense. This turns out to be 0. So that's an important conclusion. For the Brownian particle, this is for Brownian particle. Okay, this is answer number 1. Answer number 2, okay, if this is first bracket, one factor of this bracket is 0, let me find out what is square of this, again in an average sense. So I take the average or center of mass at time t minus or center of mass at an earlier time. Take the square of average. What is this? This turns out to be the following formula. When you do the mathematics calculation, as I have given in the derivation in the handout, this turns out to be 6 dt, right? Minus, let me write down 6 dm over zeta 1 minus e to the minus, again, same quantity that we had before, zeta t over m. That's the answer. I'm not deriving it. I'm just giving you the answer. And here I have introduced this quantity d. You have seen the character mass. You have seen zeta. Now I have d. What is d? This d is equal to kBt over zeta. And you have seen temperature before, you have seen zeta before. So when you do the calculation, as I told you here, I solve this equation using this input. And in an average sense, I calculate this quantity and this quantity. And for this quantity, this is the answer. And then the d is called diffusion coefficient. Okay. Now let's look at the limits of this. Okay, so when you look at this, what is the characteristic time? When you look at this problem, right away, you get by inspection, characteristic time tau is equal to, look at this, e to the minus t divided by time, that's m over zeta. Here, dt here, and the t here is m over zeta. The characteristic time is m over zeta. Not a surprise, because by looking at the shape of this equation, for even though the force is random, the characteristic time is m divided by zeta. You bring m down here, and the zeta downstates or downstates. So the characteristic time is m over zeta. So it's obvious right by looking at the equation, the starting equation. But when you do the calculation, explicit, exact calculations, you get the same answer, m over zeta. So I say, let's consider short times. When I say short times, it by itself is meaningless. This means t is shorter than tau. That's what that means. When I say short times, t is shorter than this time. If t is shorter than this time, this is e to the minus t by tau. Tau is m over zeta. So that means that this argument of this exponential is small. So I can expand that. Okay. If I expand this, the answer is, right? You can expand this quantity. The answer to maybe we should do it, right? So for this time, this is equal to, that is, this quantity is equal to, what is it? 6 dt. Okay, we'll write it to be 6 dt. We can write it like that. Negative 6d m divided by zeta. And let's expand this. 1 minus exponential. 1 minus zeta over mt plus zeta square t square with 2 m square plus etc. Close up parentheses like that. Right? I'm just expanding this. So if you do that, this one cancels with that one. 1 minus 1. Okay. Then I have negative times negative, that's plus zeta over m e. So m over zeta, zeta over m, they cancel out. I have 6 dt, the negative sign, and I have that quantity. So that means this term cancels with that term. When I multiply that term with this one, that cancels with that term. Therefore, to leading order, I'm left with this quantity times this quantity. Please notice that there is a negative sign here. Negative times positive is negative. There's another negative. So when you combine them, you get negatives times negative is positive. So I have 6d. And what is d? D is, oh, I'll write down 6d m over zeta times, please, let's do this, zeta square t square divided by 2m square. Okay. And the d is kbt by zeta. So this is equal to 6 kbt over zeta, m over zeta, zeta square with 2m square t square. So this is equal to, please look at this, 6 divided by 2 is 3, and kbt appears in here. Zeta, zeta, zeta square, here is zeta square, they cancel out. And then there's a factor of m squared in the denominator. So this is m times t square. So the mean square displacement is equal to t square. proportional to t squared with this quantity. That quantity we know from equipartition theorem. You recall equipartition theorem, half m v square, right? Half m v square is equal to what? Half m v square is equal to 3 divided by 2 kt. We know that. Therefore, 3 divided by m kt is v square. So that means this is equal to v square. So that's equal to v square average in equilibrium times t square. That means for very short times, according to this equation, this Langevin equation, the mean square displacement is undergoing Newtonian dynamics, because mean square displacement is velocity times t in the Newtonian, right? No Brownian motion yet for very short times. Therefore, square of that would go like velocity square times the time square. So for very short times, this behaves like Newtonian. As long as t is less than tau. If t is less than tau, you have this behavior. Now let's look at the case where t is larger than tau. When t is larger than tau, it's quite obvious, right? I go to this full expression. When t is larger than tau, that's the denominator here, e to the minus a large number, say 100, e to the minus 100 is 0. So this goes away. Therefore, this bracket term comes like 1. And then m over zeta is my tau. 6d t, 6d tau. Since the t is larger than tau, this is not important. Therefore, I get this result. So for long times, that means that t is much larger than tau. Then the displacement, average displacement, mean square displacement, six dt. But this is an interesting limit. This is an important limit. And this is true, right? This is true only if this condition satisfied. If that condition is not satisfied, you will not get this result. Okay. So let me plot this a long time limit and the short time limit together given by this formula. If I do this, what I get is the following. Okay, so let me plot R at T minus R center of mass spread, area times square average as a function of time. The time is time duration, how much it has displaced. Average is 0. We already did this, right? The average at the top, average is 0. But mean square displacement depends on t in a nice way. For very short times, it goes like quadratic. It is going like a t square. That's what we found from here. It goes like a t square. But for very long times, it goes like t. Linear with t. But remember, the square of displacement goes with the time, not the displacement. In the Newtonian case, if you have uniform velocity, it will go linear with time. But in here, mean square displacement is going like t. And this is different from the picture that we had here. Because for very long times, right, although this is 0, but the mean square, root mean square the displacement keeps on increasing. So if I can plot this once more in a different way so that you can compare, right? This quantity, that is R center of mass at time t minus R center of mass time at an earlier time, square of this, average it out, and then take the square root as a function of t, right? For early times, it goes like linear like this, like what you saw in Newton's case, right? Displacement, no averaging. Displacement as a function of time goes like this, linear, but instead of reaching an immobile state, now what you have is goes like this, and then keeps on going. This is square root of t. This is the t at different times, and then the break point is tau. And then you get, for long times, you get this. When you do this, you call this to be a diffusion. So the Brownian particle undergoes diffusion. This is diffusion. Okay. Right. Now let's look at their consequences. Let me go back and write down what D is. Again, once more. D I have written to be KT by zeta. So I go here, I write down D is KT over zeta. This is Einstein's research. Okay, that's the derivation. That's what he got. When you do this at the asymptotically long times, this becomes 6 dt, where d is given by this, right? So that's asymptotic result. This is, again, let me write it down again. This is diffusion. Okay. Now, 50 years earlier, there was a calculation by Stokes. What he showed was, if you have a rigid sphere in a liquid, the friction coefficient is equal to 6 pi eta naught r. Okay. Eta naught r, where r is a radius. Okay. Therefore, the diffusion coefficient is equal to kBt divided by 6 pi eta naught r. That's how we get what is called Stokes-Einstein. Stokes-Einstein's law. D is equal to KT by 6 pi eta naught r. Now here, I want you to appreciate conceptually that if I look at mean square displacement in this limit, diffusive limit, right? R square, again, R center of mass at time t, R center of mass at an earlier time square average, that's equal to 6 dt. If we look at the mean square displacement for long times, it obeys that law, that is this, and that is this. Therefore, D turns out to be KT by eta naught R. R is a radius of the particle. This is an extremely important conceptual breakthrough. Why do I say this? Mass does not appear. Mass does not appear here, right? Temperature we know, viscosity of the solvent we know, R is the radius of the particle. It is not the volume of the particle. It is not the surface area of the particle. It is linear size of the particle, right? So the movement of this Brownian particle for long times is dictated by the linear size of this object. So this is linear size. Radius, right? That's the radius, right? Linear size of the particle. In contrast to what we talked about, the beaker experiment. Remember, we had our sample in a beaker, and then the beaker is sitting on the table. There, the mass of the beaker was important in describing the movement. Going back here, I wrote down, there's a commentary that M plays a role, mass plays a role, right, in dictating the center of mass motion, because it reaches that value, V0, M over zeta, etc., etc. But that's not what we find here. What we find here is only linear size matrix. But this also gives an opportunity for experimentalists to measure this. If we can measure the diffusion coefficient, then we can measure the linear size if you know the viscosity of the solvent. So this is a powerhouse for characterizing polymers. Whenever you make a polymer, as soon as you want to know how big this molecule is in terms of linear size, we try to measure the diffusion coefficient. Right? If you measure this, then you will be able to get R. And let me tell you the experiment that it does. The experiment that is used, routinely used, to determine the linear size of a particle is to measure D. And the experiment is a dynamic light scattering. So it turns out, if, right, let me write down, right, the dynamic light scattering, right, it can be written to be the structure factor S of K. We have gone through this already. Please look up the handout before. This is the dynamic structure factor, which is proportional to the scattering intensity at the scattering wave vector K and at the time T. This can be written is proportional to e to the minus K squared divided by 6. And this quantity that we have been talking about, R center of mass at time T minus R center of mass at an earlier time square average. And that is the answer. This is the exact answer. And you know an expression for this one. This expression is this expression. We have to put all these terms into this form. We have to put everything. It's not simply 6ET. You take this expression and put it in here. But if you are sure, if you are making measurements, that there's a time measurement that you are making, time duration, that is, right, scattering after time duration T. If that time duration T is larger than tau, if you convince yourself your experiment is satisfying that condition, if it is true, then this expression turns out to be e to the minus dk squared t. Because that quantity is 6 dt, and then put it in here, 6 and 6 cancel out, dt, d comes here, t comes here. So the dynamic structure factor is a simple exponential with time. Simple exponential with time if t is larger than tau. If t is not larger than tau, then it will not be exponential in time. because then I have to put the whole function, which goes from t squared to t. So you'll have some complicated result when you make measurements. The time decay of the dynamic structure factor will not be a simple exponential. Okay. If this condition is met, you will have a simple exponential. So I write this to be equal to e to the negative rate, which depends on kt. Gamma k is a rate of decay. Decay rate, which is k dependent. And you know k is related to scattering angle, right? You remember k is equal to 4 pi over lambda sine theta divided by 2 in a scattering experiment. By changing the angle, you change k. Depending upon your particular system, you may change lambda 2, like in neutron scattering or X-ray scattering. But for characterization purposes, dynamic light scattering turns out to be pretty useful, very, very good tool. So from this measurement, which is scattering intensity, you can normalize it with 0 time equilibrium value. Here's an exponential decay, and the decay rate, right? Decay rate depends on k. So I measure, for example, I measure I of kt, that is scattering intensity, and then I normalize it with the 0 time, that's the equilibrium value. And then I plot this as a function of k squared, which is k is this. So therefore, given wavelength, I'm going to plot as a function of sine squared theta by 2, right? That's k squared. If I do this, because gamma k, right, since this quantity is e to the minus gamma k t. All right. I think what I want to do is in this plot, I want to plot as a function of t. Right? I want to plot as a function of t. Right? And the way this is gamma k, where gamma k is equal to dk squared. So if this is exponential decay, this ratio is an exponential decay, I'll plot semi-log. Take a logarithm of this, logarithm of this quantity, and plot as a linear function of t. Then what you will see is you'll see a very nice state, and data will go like this because of the negative sign. And this slope gives me a gamma k. That gamma k contains this information d. But if it's a pure diffusion, as we are talking about, there is a theorem that gamma k must be dk squared. It cannot be anything different from k squared. It has to be k squared if it's a diffusion. This will come back to polymer dynamics later on. That's why I'm emphasizing this. So you make a measurement, right? You go to a sample and change the angle, make this measurement. You collected data at different time delays. You have those data, and then you plot semi-log plot, and then you get a slope. It should be a straight line. If you are in this region, if it's in this region, that should be t. If you are not, you'll have deviations. Okay, so you have that. Then you plot this quantity. This is gamma k that you have gotten. You plot gamma k, right, as a function of k squared. As a function of k squared. And what you should do, you should get this result, because I'm repeating, right? That's what you should get. So let's plot a dk is proportional to k squared. It is not. This is not, okay, when k is equal to 0, what do you get? When k is equal to 0, gamma k is 0, somewhere here, right? But you cannot measure it, because k is equal to 0 means theta is equal to 0. So you cannot measure the intensity at 0 angle. You will hurt your instrument, right? Therefore, that is an extrapolated value. There's only a limit. So finite angles we measure then your data point should look like this if it's diffuse. So it should be a straight line, perfect straight line with a square, and then when you extrapolate it, you should go through the origin. If you do that, the slope gives me D, the diffusion coefficient. And D, I get to D, and that's equal to, of course, to KBT over 6 pi eta naught R. Measure the viscosity of your solvent and measure the temperature at room temperature wherever you do the experiment, and you have measured this, then this comes out, output. Output is size, linear size. So that's the way we do experiments and we understand Brownian motion. Now, why do I spend so much time emphasizing these results? The reason is it does not matter whether it's a colloidal particle, lattice particle, or a polymer coil. It does not matter whether it's a good solvent or a theta solvent. It does not matter whether it's a rod-like semi-flexible polymer. Right? Really does not matter what they are. These laws are valid. These general laws are valid. So we will go through polymer dynamics and we'll show this diffusion coefficient follows a similar law, depends on temperature and viscosity. Instead of this R, for a rigid sphere, for a coil, we would call, let me draw a line here, we would call in general, right, D will go like KBT divided measured D will go like 6 pi eta naught, and I'll write R and I'll write RH. This is RH is radius, hydrodynamic radius of this polymer. Okay, and we'll see this RH, we'll come back and discuss this more. This is proportional to, within a factor of 1, is proportional to radius of gyration. And you know from the previous lectures, radius of gyration goes like molecular weight power the size exponent nu. That nu depends upon the conditions, good solvent, poor solvent, etc., etc. So by making these measurements, we will be very quickly be in a position to go and say something about the size exponent and size radius of this macromolecule. For the branch molecule, flexible molecule, good solvent, poor solvent, polyelectrolytes at high enough salt, right? Etc. Semi-flexible chains, we can characterize them by using this technique. And I also mentioned in the last lecture, there is also a bonus result coming from Einstein. He, in a separate paper, he showed, okay, these particles are moving around. The particle undergoes diffusion, and the diffusion can be characterized like this. At the same time, the viscosity of the medium is also changing, right? So how does it change? The viscosity of the medium, he showed, as I explained in the last lecture, viscosity of the solution now minus viscosity of the solvent divided by eta naught. That goes like some number for a rigid sphere, right? Volume fraction, right? There's a number of chains by V times 4 by 3 pi R cubed. R is the radius, that's the volume of one sphere. There are n spheres. N is number. N is equal to number of spheres. V is volume. And you know R is radius. So this goes like, forget about 5 by 2, 4 by 3 pi. This goes like N over V R cubed. This is Einstein. Okay. In general, I'll say, just like what we did. Again, once more, please notice it's only a radius that matters, right? Radius. In this particular case, since I'm writing in dimensionless units, it's a volume fraction. In general, I can write this eta minus eta naught by eta naught to be equal to n over v times, say, Rg cubed, for example, for the polymer. It's general. In a rigid sphere, I could write Rg cubed. And all the prefactors, numbers, the number is not going to be 5 by 2, but that's somewhere here, which we'll return to this. Now, what we say is, oh, that's a general result. What we can say also is, I can write, polymer concentration. We always write polymer concentration C to be number of chains, number of molecules, times molar mass, if you like, or maybe I write molar mass. If you write in gram per cc, something like that, molar mass divided by V. That is your concentration. If that's the case, I go back here, rewrite this. This is equal to N M by V and Rg cubed by M. I multiply it and divide by M. This is the change in viscosity. So that is equal to concentration power Rg cubed by M. And that's equal to concentration. What is Rg? We already talked about molecular weight power 3 nu. Rg is molecular weight power nu, and therefore Rg cubed is molecular weight power 3 nu. And then here is a factor of M minus 1. Without doing any calculations ourselves, we have come up with a very simple prediction based upon this beautiful calculation done by Einstein. M power 3 nu minus 1. This is a very general result, which we will derive. We will talk about it later on. This is true in general. Theta solutions, good solutions, semi-flexible chains, polyelectric solutions, high concentrations, low salt concentrations. You get this way. And I can assure you that this is correct. Experimentally, we verify that. Okay, we will talk about that down the road. After you follow these concepts, we will do them. Okay, so I think I'm going to stop. I like to stop here. Let me stop sharing unless there are.